Welcome viewers. In this video we will see the coupled circuit parallel connection in that parallel aiding. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. Parallel connection in that parallel adding. Consider this circuit. Two inductors are connected in parallel, L1 and L2. V of t is the supply voltage. Then current I of t is flowing from the supply. At this point the current is divided, I1 and I2. The dot is available here. In both L1 and L2, current enters in the dotted section. At dots the current is enters. So due to this it is coming under aiding. The inductance, mutual inductance is added together. This is a mutual inductance M between L1 and L2. Current enters in the dotted end. So it is coming under parallel aiding. Both current I1 and I2 enters the coil at the dotted terminal. Now by using the KVL we can frame the equation for L1 as well as L2. So this is considered as L1 and this L2. The supply voltage V of t, both L1 and L2 connected in parallel. So the V of t is applied to L1 as well as L2. So the supply voltage V equal to inductive drop L1 di1 by dt plus M di by 2 di2 divided by dt. So this mutual inductance in the coil L1 is due to second coil, that is second coil current I2. So inductive drop of L1 we are using I1, for mutual inductance we are using I2. This mutual inductance is due to the current in the second coil, so that I2. Similarly, while referring the second coil L2 di2 divided by dt, in that the mutual inductance is due to the first coil current I1. So that M di1 by dt plus L2 di2 divided by dt. Right? So inductance L1 in that mutual inductance due to the second coil current I2. This inductance L2 drop in that mutual inductance is due to first coil current I1. Right. So this will take this equation 1 and equation 2. The same thing we can write in a sinusoidal form. This equation 1 can be written as j omega L1 I1 plus j omega M I2, that is equal to V. In a excitations are sinusoidal, so the above equation can be written. Similarly, equation 2 is written as j omega M I1 plus j omega L2 I2 equal to V. So this will take this equation 3 and 4. From the equation 4, we can find the expression for I2. Now we take the equation 4, j omega M I1 plus j omega L2 I2 equal to V. Bring this term that side, so that V minus j omega M I1. Bring these terms j omega L2 in the denominator of that other side, so that V minus j omega M I1 divided by j omega L2. Now we got the expression for I2. Now we are going to substitute this I2 expression in equation 3, so that we are able to find the value of I1. Right? So substitute I2 in equation number 3. Now we'll see how we are substituting. So this is equation 3. J omega L1 I1 plus j omega M I2 equal to V. This I2 we are going to substitute this value. Then it is multiplied inside. J omega M V divided by j omega L2 minus j available 2 times, j square omega also available 2 times, omega square, M also available 2 times, M square I1 divided by j omega L2. Right. So here j omega got cancelled. Here one term got cancelled. Here j square omega square available. Here j omega available. One term got cancelled. So after cancellation, what we got? This j omega L1 I1 plus Vm divided by L2 minus j omega M square I1 divided by L2, that is equal to V. Now j omega I1 available in both the terms. So taken outside. So L1, here L1 is there, here M square, here L1 is there, here j omega I1 M square by L2 is available plus this term Vm divided by L2 equal to V. Right? J omega I1 is taken outside. Now we'll go for the further simplification. Now this Vm by L2 is brought that side. So minus Vm by L2. So this will take this LCM L2. So that here L2 are not available. So multiplied V L2 minus Vm divided by L2. Now bring these terms. In order to find the I1, bring all these terms in the denominator. So VL2 minus Vm by L2 into this L2 goes to the numerator. L2 goes to numerator. This term goes to denominator. L2 divided by L1 L2 minus M square into J omega. This J omega. Here also LCM is taken. L2 is taken LCM. Here L2 not available, so it is multiplied. L1 L2 minus M square. Both the side. Here also LCM taken and here also LCM taken. Right. So L2 L2 got cancelled. So what we have, V L2 minus Vm divided by L1 L2 minus M square into J omega. In order to bring the J omega in the numerator, it is multiplied and divided by J omega. J omega multiplied and divided. Now we'll see how we are simplifying this expression. So this J omega is available here. J omega into V L2 minus Vm. Here J square omega square. J omega available 2 times. J square omega square. We know that J square value is minus 1. So it is now it will become minus. So due to this minus, it is multiplied inside. So it become M square minus L1 L2. Right. So I1 equal to J omega V L2 minus M divided by omega square into M square minus L1 L2. Right. Now we got the expression for I1. So similarly we can write the expression for I2. Same thing we can write here L1 minus M. Only the change. Here L2 minus M. I2 is written L1 minus M. Right. So now we got the expression for I1 and I2. So that we can able to find the total current. I. Total current I we can calculate. I equal to I1 plus I2. So this expression is written. Only here L2 available, here L1 available. Now we'll take the LCM. Both the terms are common. So both are added together. Right. Now we can multiply. Now J omega V is available commonly. This is taken outside. So what we have, L2 minus M plus L1 minus M. So that L1 plus L2 minus 2M. M available 2 times with negative. So what we have, J omega V L1 plus L2 minus 2M divided by omega square M square minus L1 L2. Now we'll go for the further simplification. The term available V is brought in the denominator this side. So that I divided by V is available this side. Now it is written in the reciprocal V divided by I, because impedance is V divided by I. So that it is written numerator and denominator are interchangeable. So this omega square, this term available in the numerator, this term now available in the denominator. Now we know that V divided by I is impedance. So that it is written Z equal to V by I, this term. In order to bring this J, again it is multiplied and divided by J. Multiplied and divided by J, so that we can go for further simplification. So what happened here? Omega square into J, this J is available, into M square minus L1 L2. Here J available 2 times. J square omega L1 plus L2 minus 2M. J square is minus 1. We know that J square is minus 1 and omega 1 term got cancelled. Right. So what we have, minus J omega M square minus L1 L2 divided by L1 plus L2 minus 2M. Right. Again we will multiply this negative inside. So that it become L1 L2 minus M square divided by L1 plus L2 minus 2M. Right. Now we got the expression for V divided by I. After all simplification we got this value. Let LA be the equivalent of the combination of inductance. We know that two inductance L1 and L2 are connected in parallel. So the equivalent inductance we will take LA. So that V divided by I equal to J omega LA. So this LA is nothing but this term. By comparing these two, This LA is the what we got in the simplified expression. This is the LA, equivalent inductance. So LA equal to L1 into L2 minus L square divided by L1 plus L2 minus 2M. So the two inductors connected in parallel, and it is series adding and parallel adding, that is current enters in both the dot, so that it is coming under adding. Both the mutual inductance are added together. In that case, this is the equivalent inductance, L1 L2 minus M square plus divided by L1 plus L2 minus 2M. So in this video we got the equivalent inductance of parallel combination of coupled circuit in the case 1 series adding. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening.